Okay, so for this recording, we're going to talk about Taylor and McLaren series. Well, we're kind of not, but we kind of are. So first of all, what are the Taylor and McLaren series? So let's suppose f has derivatives of all orders on an interval containing the point A. The Taylor series for f centered at A is given by f of A plus f prime of A times x minus A plus f double prime of A over 2 factorial times x minus A squared, right? And so if we wanted like sort of what does the nth term look like, it's the nth derivative over n factorial evaluated A x minus A to the n plus the, and this goes on forever and ever, so we can write this as the summation and goes from 0 to infinity. The nth derivative evaluated A divided by n factorial x minus A to the n. And if A is equal to 0, the Taylor series is called the McLaren series, so that's the big deal. Before we actually start playing with Taylor and McLaren series, I'd like to just play with something that's a little more finite, actually finite, and that would be the Taylor polynomial. So the Taylor polynomial, we only need the first n derivatives to be, let's say, defined at A. And the nth order Taylor polynomial for f, which its center at A, is denoted by p sub n. And so p sub n of x is going to be, well, you know, basically we take the first n plus 1 terms of the Taylor series. So we have f double prime of A over 2 factorial x minus A squared plus the difference being here is that we actually stop at the nth derivative. Now we can still write this in series notation, right? We can write this as the sum k goes from 0 to n of the kth derivative of f over A divided by k factorial times x minus A to the k. But what I want to spend most of the time here is working on a couple of examples. Let's find the nth order Taylor polynomial for f of x equals log of x centered at x equals 1. So that's our A. And so basically what we need to do is we need to find a pattern for these things, just like when we were working with series, like we were working with sequences, well, and series. Okay, so first of all, f of x is log of x, and we're interested in evaluating everything at x equals 1, so f of 1 is log of 1, which is 0. F prime of x we know is 1 over x, so we know f prime of 1 is 1. F double prime of x is negative 1 over x squared, which we can write as negative x to the negative 2. And we see that f double prime of 1 is negative 1. I recommend at least 4, sometimes 5 derivatives, just so you get a feel for things. So the third derivative is going to give me a 2 x to the minus 3. So my third derivative at 1 is 2. My fourth derivative is going to be negative 3 times 2 x to the minus 4, which you can think of as 3 factorial. So my fourth derivative at 1 is just negative 3 factorial. Let's do one more just so we make sure we have a good feel for what's going on. I'm going to have a negative 4 times negative 3 factorial x to the minus 5, which is just positive 4 factorial x to the minus 5. So my fifth derivative at 1 is just positive 4 factorial. So if you kind of look at these, you can see that the nth derivative looks like it's going to be, well, we have n minus 1 factorial, because right when n is 5, we have a 4. When n is 4, we have a 3 factorial, etc. We also have the negatives going, and notice that when n is odd, we have a positive, which tells me I'm going to have a negative 1 to the n plus 1, x to the negative n. Now, one thing we want to notice here is we have an n minus 1 here, and also notice that negative 1 to the n plus 1 is equal to negative 1 to the n minus 1, if n is 1, 2, etc. So we can use that when we're writing the nth derivative of 1, right? Instead of writing n minus 1 factorial negative 1 to the n plus 1, we can write negative 1 to the n minus 1 times n minus 1 factorial. Okay, so what's our Taylor polynomial? What am I doing? Dot, dot, dot. We're stopping. So Pn so Pn is, right, f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial x minus 1 squared plus nth derivative of 1 over n factorial x minus 1 to the n. So plugging stuff in, I get 0 plus 1 times x minus 1 minus 1 over 2 factorial times x minus 1 squared. Let me put the third derivative in, right? Because I got a 2 factorial over 2 over 3 factorial x minus 1 cubed plus dot 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 plus negative 1 to the n minus 1 factorial over n factorial x minus 1 to the n. So as we hopefully remember, right, 3 factorial is 3 times 2 factorial. And so that means that we get to cancel out because 2 factorial is 2. And similarly, n factorial is n times n minus 1 factorial, right? Because we worked on this stuff in the previous chapter. I think that was called chapter 5. And so these guys cancel, which allows me to simplify my series and write x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed plus dot 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 plus negative 1 to the n minus 1 over n minus 1 x to the n. And we can write this in series notation, right, with this in sigma notation, any year now, with, k equals 1 to n. So we have a negative 1 to the k minus 1 divided by, wait a minute, that's 1, that's 2, divided by, I lied, that's an n, isn't it? It's always good to actually keep track of your own work, because that's an n. Divided by k, divided by k, oh, for heaven's sake. X minus 1 to the k. Okay, great. So let's use the approximation for n equals 0, 1, 2, 3, just to approximate log of 1.1 and find the absolute error. Remember, the absolute error is I take my approximate answer minus the actual answer, but take the absolute value of that. So what is P0 of x? Well, P0 of x is 0. So that would mean that my approximation for log of 1.1 is approximately 0. What's the error? Well, the error is equal to 0 minus the actual log of 1.1 in absolute value, which is approximately 0.0953. So taking like 0 terms of my series works really well. If n is equal to 1, then I get just the first term, so x minus 1. So natural log of 1.1 is going to be approximately 0.1. Because if you'll remember, P sub n of x is approximately log of 1 plus x. And so p sub n of 0.1 is approximately log of 1 plus 0.1 or log of 1.1. So we're doing good here. We're making progress. So here our error is going to be 0.1 minus the log of 1.1, which my handy dandy calculator told me was about 0.469 times 10 to the negative 3. And for comparison, this is about 9.53 times 10 to the negative 2. All right, let's try P2 of x. P2 of x is going to be x minus 1 minus 1/2 x minus 1 squared. So log of 1.1 is going to be approximately, wait. What did I just do? Wait a minute. Sorry, Pn of 1.1 is going to be log of 1.1. So I have 1.1 minus 1 minus 1/2 times 1.1 minus 1 squared, which is approximately 0.0095. And what's the error on this one? So I have 0.0095 minus log of 1.1, which is approximately 3.1 times 10 to the negative 4. Last but not least, P3 is x minus 1 minus 1/2 x minus 1 squared plus 1/3 times x minus 1 cubed. So log of 1.1 is approximately P3 of 1.1, which is approximately 0.09533. I don't know where that extra 0 came from there. Apparently plugging numbers into the calculator, typing them, and then reproducing them, not my strong suit. Okay, so the error for this one is absolute value 0.09533 minus log of 1.1, which is approximately 2.32 times 10 to the negative 5. So one thing you might notice, and I noticed right away, is that the sort of the powers of the error are going down, right? We have what do I mean by powers? I mean the error is improving by an order of magnitude, right? Because we go from -2 to -3 to -4 to -5. So the polynomial could be useful depending on, well, a couple things. So first of all, the polynomial can be easily computed. So it could be used to approximate the function sort of on the fly, right? If you don't have a calculator that does natural log, don't know why you wouldn't in 2020, but let's just say that you left your phone at home and someone asked you to calculate log of 1.1 and you didn't have a calculator. So you would be just like, let's do the second Taylor polynomial. That gives me an error about 10 to the minus 4th. All right, that's really good approximation. So also, of course, you can't really do an infinite series. Where do you stop? Oh, wait, that might have to do with something about remainder. All right, here we go. So let's talk about estimating. What did I miss? Estimating the remainder in the Taylor series. Or in a Taylor polynomial, sorry. So the remainder is the difference between the function value and the polynomial. Right, so it basically gives us some measure of the error approximating the function. So what is that remainder? So if Pn is the nth order Taylor polynomial centered at A, and if the first n plus 1 derivatives are continuous, then the remainder is the n plus first derivative evaluated at a point C, n times n plus 1 factorial over x minus a to the n plus 1. Where C is something we don't know. But what we do know is it's between x and a. And why is this? So like the actual proof, if I were feeling like an actual proofy moment, which I'm not, but sort of the reason that this works is because f of x is equal to f of a plus the integral from a to x f prime of t dt. So we would start with that. Let me move that down so my start with comes actually under the y. And then what we would do is we would do integration by parts a whole bunch of times. Let's just say n times, since we're talking about the nth polynomial. And then we would use the integral mean value theorem. Y'all remember that mean value theorem. And so again, what is C? We have no idea. We don't actually know. It depends on the problem. But it's not something you can actually find. So let's do a quick example of finding the remainder term for the nth order Taylor polynomial centered at 0, approximating f of x equals sine of x. So the Taylor polynomial for f of x sine of x is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus -1 to the 2n plus 1 x to the 2n plus 1 over 2n plus 1 factorial. I guess I don't know why I have that. -1 to the n plus 1 or n minus 1. However you feel like doing it. This is really a pain. So let's not do it this way. Let's pretend that we don't actually want to figure out the polynomial. We just want to know how good we can do, because this is figuring out the polynomial. But without even knowing anything, I know that the remainder is going to be the n plus first derivative at C over n plus 1 factorial x minus a to the n plus 1. So I know that it's going to be the n plus first derivative of sine evaluated C divided by n plus 1 factorial x to the n plus 1. And so the n plus first derivative of sine at C is going to be plus or minus cosine C or plus or minus sine C, depending on n. We know that. All right, but how do I estimate the remainder? Because usually I don't really care exactly what the remainder is. What I most care about is figuring out what's like the worst the error is going to be. So if I suppose that the derivative, the n plus first derivative, is less than or equal to some constant m, I can bound the absolute value of the remainder by this m and then absolute value everything else. So let's just look at an example. Specifically, we'll do our error approximating log of 1.1 using the fourth order Taylor polynomial of log of x centered at a is equal to 1. So we already know what the log of x, what p sub n of x looks like, right? P sub n of x is the summation and k equals 1 to n. Oh, pity's sake. Yeah, summation k equals 1 to n of -1 to the n minus 1 over n over k. Everything's k, x minus 1 to the k, because we figured that one out. That was like 2 examples ago. So from a previous example. Okay, so my remainder is going to be what? So R4 So this is telling me, sorry, first of all, that log of x is going to be this guy, which is x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. Here n is 4 minus 1/4 x minus 1 to the 4th plus the remainder. And so our remainder from above is going to be given by the 4th derivative of f of x evaluated c divided by 4 plus 1 factorial x minus 1 to the 4 plus 1, also known as the 5th derivative, over 5 factorial times x minus 1 to the 5. So what is the 5th derivative of x? Of f, that's just the 5th derivative of log of x, which is 4 factorial times x to the negative 5th. And so that tells me then that the 5th derivative at this point c is going to be 4 factorial times c to the negative 5th. And c is going to be between, well, a, x, and 1.1. And so what's a bound on this? So I'm just going to have 4 factorial over absolute value of c to the 5th. And this is going to be less than or equal to 4 factorial since c is greater than or equal to 1. Okay, so a bound on my remainder then, since x is equal to 1.1, I believe, that's where we were doing it, 1.1. 1.1 is going to be less than or equal to, okay, so we have 4 factorial from this guy here divided by 5 factorial. That's just copying our formula here. And then 1.1 minus 1 to the 5th, since x is 1.1. And so this is, well, actually 1/5 times 0.1 to the 5th, which is equal to 2 times 10 to the negative 6. And so that is our remainder approximation. And I have one more example, so I guess that's going to make this the video from heck. So I apologize for that. Find the minimum order Taylor polynomial needed to estimate 1 over 1.25 with an error of at most 10 to the negative 3. So we can think of 1 over 1.25 as 1 over 1 plus 0.25. Which we can look at as 1 over 1 plus x, at x evaluate as x equaling 0.25. Okay, so what we're going to do is we're going to let f of x be 1 over 1 plus x and determine the Taylor series of f of x centered at a equals 0. So in other words, we're going to find the McLaren series. All right, so just like we did before, we'll make our list. So f of x is 1 over 1 plus x, or 1 plus x to the negative 1. F of 0 then is going to be 1. F prime of x is negative 1 plus x to the negative 2. F prime of 0 is negative 1. F double prime of x is going to be 2. 1 plus x to the negative 3. So f double prime of 0 is 2. The third derivative is going to be negative 3 times 2, 1 plus x to the negative 4, which is negative 3 factorial, times 1 plus x to the negative 4. So f third derivative at 0 is going to be negative 3 factorial. And I'll just do one more for good measure. I have -4, but you may recognize that this is super similar to the example that we just did. And so this is 4 factorial times 1 plus x to the 5th. So the fourth derivative at 0 is 4 factorial. So hopefully you can see that the nth derivative evaluated x is going to be -1 to the, I think it's n this time, right? Because when n is even, right, we have positive, and when n is odd, we have negative. So we're going to have a -1 to the n, and we have an n factorial, 1 plus x to the n plus 1. So the nth derivative at 0 is just going to be -1 to the n times n factorial. Okay, so our n plus first derivative evaluated x is going to be -1 to the n plus 1, n plus 1 factorial, 1 plus x to the n plus 2. And so, right, when I evaluated c, I'm going to get, well, everything's going to stay the same, except it's going to be replaced by a c there. And what do we know about c? It's between 0 and the x we're evaluating things at, which is 0.25. And so our derivative then is going to be bounded. Oh, come on, erase. I think methinks my computer is getting tired. Maybe I should save everything for a minute and then it'll be happier. Okay. So what's the worst possible case for this thing? Well, first of all, oh, these are all negative powers, aren't they? Sorry, that's a negative n plus 1. So that's a negative n. Boy, that sure makes a difference, doesn't it? So when I take the absolute value, what's going to happen? So first of all, the absolute value of -1 is 1. N plus 1 factorial is its own absolute value. And I'm going to write this in the denominator. C is between 0 and 0.25, so this is always positive. And so, but this is less than or equal to n plus 1 factorial. Again, since C is somewhere in there. Actually, it's less than. Okay. So that means our n plus first, the error in P sub n, right, the remainder is equal to what? Well, it's the absolute value of the n plus first derivative of c divided by n plus 1 factorial times x minus, here a is 0 to the n plus 1. And so we just showed that this is going to be less than or equal to, so we have the n plus 1 factorial for the derivative over n plus 1 factorial times x to the n plus 1, which is just x to the n plus 1. So we need to determine n so that this remainder is less than or equal to 10 to the -3. So in other words, we need Well, x, we know x. So specifically, right, we're looking for the remainder of 0.25 to be less than or equal to that. Please be nice to me. Please be nice for just 2 more minutes. So 0.25 is 1/4. So I have 1/4 to the n plus 1 less than or equal to 10 to the negative 3. If I were to take some algebra real quickly and multiply both sides by 4 to the n plus 1 times 10 cubed, right, what am I going to get? I'm going to get that 4 to the n plus 1 is greater than or equal to 10 cubed. So by trial and error, we find that n equals 4 gives an error or a remainder of 0.25 to the negative 5, which is 1/4 to the 5th, which is approximately 9.8 times 10 to the negative 4th. So n is equal to 4 is what we need. And that's it. So next time we're going to look at Taylor and McLaren series expansions of common functions. And we're going to call it very long, and I apologize for that.